This is the presentation in week one in the lab, and my the items that I want to discuss are basically two problems out of the book. One is the concept of applied load when it is the acceleration that's acting, or gravity, for example, and the other one is an enforced displacement that you'll see popping up in the second problem. All right. This is my first problem, and you have an I-beam which is clamped at one end and it's deflecting under its own weight. Okay. Please keep in mind that if the I-beam is very long and with thin uh, web and uh, flange, then this is not the kind of element that you want to use. But at this point, we don't have anything but solid elements, and we're going to be solving this problem. Now, when you look at this, it is obvious, I hope, that the YZ is a plane of symmetry. Many of you may think that actually XZ is also a plane of symmetry. It is not. Or even XY is a plane of symmetry. That is not the case. With this geometry, the restraint specified and the gravity loading, the YZ is the only plane of symmetry. Incidentally, if left side and right side will both clamp, then YZ and XZ would then be both planes of symmetry, but not in our case. All right, so I'm going to be making this part, and in the lab when I did this thing, I totally ignored dimensions, but I'm not going to do that here. So let me go ahead and create a part file, and immediately I'm going to save this thing. So file, save management, save as. Let me see now, desktop, there is a May 10. Okay, so we're going to make a new folder, and I'm going to call it I-beam. This is going to be my first problem. I-beam weight, self-weight basically. And so everything is going to go into this folder for that particular problem. And let's go ahead and make it. Now on the vertical plane, I will sketch something that looks like the I-beam that I had in mind. Let me try something randomly here, and we're going to put dimensions later on. Okay, good. Now, I want to have an idea of what my units are. So let me dimension this thing, see what it says. So it looks like this is millimeter. That being the case, what I'm going to do, I'm going to change my units right now. So tools, options. I'm going to change this into millimeters, inches. And that being the case, I'm going to change the stress or pressure, both of them. Let's see now, where is it? Let's sort this out by clicking on magnitude. So we go to pressure. There we are. I'm going to change that thing to PSI. That's all I'm going to do. Pressure PSI. I think that will change the stress display too. So let's see now, where is PSI? Ampere square inch, right there. Okay, good. Now, this is right now 2 inches. So the drawing that I showed you shows that that is actually 1 inch, and this is 0.25. So let me dimension these first. Let me dimension, you know what? Actually, before I do that, let me make this thing nice and symmetric with respect to that line. So left line, control, right line, control middle axis. You go to right there, make it symmetric. Very good. And this line, control that line, control middle axis, also go there symmetric. Okay. Uh, right. Now, let's see whether we can put dimensions here. So this height is 0.25, 0.25 inches, 0.25 inches. Very good. This is also 0.25, 0.25. All right. And this is also 0.25. Very good. And this height up there is actually, based on the drawing, 1 inch. Yep. Okay, so the height from here to here is 1. Let's dimension this. From here to here, it is 1 inch. And there we are. This is our I-beam exit. And let me pad it by the total length of 10 inches. The direction doesn't matter. Very good. And incidentally, because of symmetry, there is one plane of symmetry, so I'm going to split it with that vertical plane. So let me go and get my saw or the split icon, surface-based feature, right? And use this, and it doesn't matter which side we pick. We can pick this side or the other side. If you're not happy with this side, just flip the direction of the arrow and take the other side. It makes no difference. There we are. Okay. We were going to make this thing out of steel, although problem doesn't say what it is. So let me use the steel here. Apply material. Let's see now, steel on that top, on the part or any piece that you anything from the tree that you select is going to put it on the whole part. Now, they installed the Service Pack 7 for me, so it used to be that when I double click on this thing, it would crash. But now when I do it, it won't crash. You select the Analysis tab, and these are the default values for a steel in SI units, so you can change anything that you don't want, but I'll keep it the way it is. Very good. We're done. So let me click on the floppy so that it's going to be saved. And now we're going to go to Analysis and Simulation, Generative Structure Analysis. Next week, we're going to talk about beam element because in all likelihood, this is not the kind of element that you use for the product. Now, I will use the default values. Double click, it's a parabolic with that size. This is a huge element size. I'm going to change this thing also 0.3, 0.2, otherwise just keep it the way it is. And right click mesh visualization. There we are. Now, if you don't see your elements, they're there, but change your rendering. Change your rendering to this third one, shading with edges. There we are. Okay. So there we are. Let me deactivate the mesh. All right. So this is a plane of symmetry. I'm going to put surface slider here, right there. One of the ends is clamped, so let me take that end to be clamped. Not the point, not the point. If you select that point again, you get rid of it. Actually, can I clear it? Remove all support. I want the face. This entire face is clamped. It's rolled. Okay, as far as the load goes, it's this. It looks like a sphere with an arrow pointing down, so it reminds you of gravity. Actually, when you click on it, it says acceleration. Because if you think about it, gravity or self-weight is an acceleration that we are applying. So anyway, so we select anything that we select because it's a body force is set. Even if I try to select this corner point, the whole thing will be selected because gravity is a body force basically. And right now, based on my drawing in the global Z direction and the value in SI units is 9.8, but in this unit it's going to be 385-ish. And if you wonder how we got 385, you take 32.2 that you all know feet per second squared, multiply by 12, you're going to get roughly 385 or 386. I'll use 385 with a negative sign to point in the downward direction. There's the gravity effect. Let's save our analysis file, save management. The analysis is not saved, save as in that same folder, which is called I-beam weight analysis 1. We're just going to put it there. And that's pretty much it. So let's go ahead and run it. Yeah, this is a warning that you get because you use surface slider. I don't like it, but they won't get rid of it. Okay, there. So look at the deflection, the deformed shape. There it is. That's the way it should be, right? If this is going under self-weight, that's the way it should be. And like that. If you want to know the value of deflection, displacement, just click on it. And this is in the form of symbols. If I want color, basically, select average ISO and change the rendering to material shading. There we are. Okay. So it's a very small amount because after all, this is a 10-inch long I-beam deflecting under its own weight on one end of it is clamp. You don't expect anything big. So if you look at the Mamisa stress, this is where it is. The biggest stress is, of course, at the wall, as we expect in beam theory. Okay. Now, just keep in mind that if this was actually not under gravity, suppose this was the antenna, I mentioned that like so in the class or in the lab, that if this was the antenna on my car, old antenna on my car, and the car was accelerating, so it's not the gravity that making this bend, it's acceleration that, of the car that makes this thing bend. So you know to apply acceleration. So you know the pressure, you know the force, and now you know the acceleration. Okay, good. So that takes care of the first problem. Now let me save this thing and get out of it, get out of it, and then we go to our second problem. The second problem is a C-clamp, like so, and the inside of this hole is all clamped, fixed clamp, doesn't go anywhere. And what I'm doing is I'm saying that suppose I take this face and somehow I make every point on it to move by 0.01 inch down. Okay, now let's not worry about how to do that, but suppose we did. First of all, we don't know how much force is necessary in order to inflict that kind of a deformation. And that's going to be part of the calculation that CATIA will do for us. Yep, aside from that, if I knew the force, I wouldn't have to do anything else. I just apply the force, but we don't know what it is. So this is called enforced displacement. You will see that you're giving it a value. You're saying, okay, this is the amount of displacement of something, maybe a point, an edge, or face, etc. What is the force needed later on to inflict that deformation? Okay, so notice that in this particular problem, we have only one plane of symmetry, and that is meaning that width-wise, we need to take only half of it. Okay, so first I will do it without a plane of symmetry, or just model the whole thing, and then I come back and do it with single plane of symmetry that we've got. Now, also it says use a local mesh refinement, or finer mesh around the area that's critical to the problem. In this particular problem, you can see that the critical area is around the bend right here. So we come back, or at least when I'm doing it right now, I'm going to make a finer mesh in this area. Okay, so let's go ahead and do this. We go here, start with the part file. There we are. And immediately I'm going to save this thing. So file, save management, save as. In that folder, which is called May 10, we're going to create another folder called C-clamp. C-clamp, and say OK. So everything for this problem is going to go into that folder. All right, let's go ahead and make it. So on that vertical plane, I will sketch something that resembles that C-clamp. I'm going to worry about dimensions in a minute. Okay, these are nice and concentric. We're going to dimension these things according to what I have there. So this dimension, it looks like this is, well, let me look at this document. 3 inches, 3 by 1. Okay, so let's go there. So this is going to be 1 inch. One. Okay, and this is going to be 3 inches. All right, and then I have a circle here, and the distance from that point to that end, I think is point 5, or if it's not, just use 0.5. All right, and then the radius of that circle, based on the drawing, is 0.25. Radius 0.25, diameter 0.5. Yep. Very good. Exit, padded. I'm going to do mirror extend because later on I'm going to take half of this. So, and in each direction is going to be 0.5. So the total thickness of 1, I believe, 0.5. Yeah, I think that's correct. Very good. So this is made out of steel, or let me assume that it's made out of steel because I didn't specify what it is. So let me go ahead and apply material to it. Steel on that part. Yeah, and say okay, and save it and get out of it. Later on, in the second round, I'm going to come back and cut this thing into 2 pieces or split it into 2 pieces and do half of it basically. So now we're going to go to analysis and simulation, generative structure analysis. It's a static analysis that we're doing, but I'm going to change the rendering so that I can see this thing better. Now you're told that I want to find a mesh in this area. How do you do that? Let me show you. You see this toolbar which says Model Manager? There's a traffic light here, kind of. The second set of icons is going to be something like this. And this says local mesh side. You see that? Local mesh side. You click on it and it says, where do you want to have a finer mesh? Well, I want to have a finer mesh in this area. And right now, the value that it uses 0.07, that's too tiny. I'll make it how about making it maybe 0.1. Let's see what happened. Yeah, right there. You can see finer mesh there. That's up to you in a sense that unless you're asked, given instructions, you do whatever you want. Right click mesh visualization. So you go here, right click mesh visualization, and you see that it's a finer mesh in this area. But deactivate this. Okay, good. So we are told that the inside of that hole is clamped. And there we are, it's clamped. That face is clamped. And you're told that on this face, you're applying a load such that it moves every point on it by a certain amount. Now in CATIA, this is called enforced displacement. You're giving me a displacement, value of displacement. And in CATIA, in order to apply enforced displacement, the first thing that you do is you say, hey, instead of 0.01 that I want, I make it 0. And how do I do that? Using restraints, using the user-defined restraint, you select this and say in the direction Z that I want to change later on, I want to fix that. That's the first thing. I don't want to fix that. I want to give it a displacement of 0.01 inch downward, but you have no choice. In CADIA, first, you have to say, I want to give it to 0 displacement in that direction, then you can change it. So how do I change it? I go here under a load, see that, under a load? This was pressure, this was force, this was gravity. You go to the fourth one from the left, it says enforced displacement. You click on it, and it says, okay, where is that thing that you want to change? Well, I want to change those restraint that I applied. You can do it either from the tree or from the screen. See that? Either from the tree, right there, or from the screen, either way. And it says, okay, what do you want it? I want it to be negative 0.01 inch. Negative because it goes downward. And let's save an analysis, file, save management, analysis, save as. This is the right folder, your May10 CCOM. That's very good. It's going to go in there. And now we're going to run it. Run. or compute. Hopefully there are no issues. Very good. Okay, so look at the deformation. There's a deformation on the image toolbar. You can animate it, a strip of film here. There we are, that's the way you should behave. You want the stresses, you click on that, von Mises stress, change the rendering if you want to see nice colors. There we are, biggest stress in this area as you expected it, etc. Incidentally, if you want to see your elements here also for some reason, what you do is you go to the rendering at the very bottom, question mark, and because this is already checked here, the elements will also pop up. Good. Now, that was not the whole problem. The whole problem, well, and part of the problem was, okay, tell me how much force I need in order to give this displacement. All right, so that, in order to do that, this is what you need to do. You go to this, you go to the tensor, not tensor, sensor at the bottom of the tree, right click, and you say create resultant sensor. See that? Go to sensor, right click, create resultant sensor, and say reaction sensor. You click on it, and it says, okay, what is it that you want me to tell you what the force is? It's this, you see that? It's this thing that I said go down by 0.01. Right? It's this thing. Yes, you select it and you say update, and you're going to get 359, roughly 359 pounds in the downward direction. That is the force. Now, don't say cancel, because if you see a cancel, there won't be any record of this that you have done. So say okay, because when you say okay, then it appears in the tree, and I can, when it comes to marking your papers, I also know where you got your number from, right there. That is the force needed to push this face down by 0.01 inch. It's going to be roughly 360. Now, this is fine, except that I want to use planes of symmetry. So there's two things you can do. You can either, well, we can go and massage this, or you can just close it. If you won't close it, go back here and I'll split it. I did not have to do that, but let me do it. Split which plane? The middle plane, and it doesn't matter what side. So now it's going to take half of it. Okay? So let me save this. It's a good idea to save this thing in a different folder in case you wanted it. You don't want to mess up your thing. I'll leave it to you. Now you're going to go to analysis and simulation, generative structure analysis, static analysis. Let me change the rendering here. Now, inside of this is fixed, means clamped. Okay. Oh, by the way, I wanted a finer mesh here, so let me take the finer mesh in that area. I'll use the same number. Okay, very good. Now, you can display your mesh if you want, but I don't want to do that. So I want to push this thing down by 0.01 inch. So first I make it 0 down. Click on the user definer strain. On that face, 0 in the third direction. Fix it. The reason it knows because a minute ago we did this. And then enforce displacement. Select that. And then say 0.01 downward. Please don't divide this thing by 2 because you took half of it. No. Okay, that's pretty much it. Let's save the second run. File, say management, analysis, save as. I'll put down here next to it symmetry used. Change the name. Okay, very good. Let's run it. Oh, I forgot something major. Surface slider, lot of lots of losing lots of marks. So click on it. Surface slider. Otherwise, it's wrong. You're going to lose marks on that. I run it again. Completely. Just taking half of it is not good enough. You have to put a surface slider there too. Good. Deflection, needless to say, supposed to look like that. No problem. Okay, stress. Okay, they should be very close to what we did a minute ago. Change the rendering. to material shading. Okay, these numbers should match your previous results very well. Now the force. So let me remind you what we did. Right click, under sensor, right click, create resultant sensor, create reaction sensor, and select that thing that you are trying to find reaction of right there, the second thingy right there. See that? Second thing, and then update result. That should not surprise you. You get only half of what you got before. The reason is that it takes that much force push this piece down, but there is a second piece on the right of it that we are not modeling. So if you multiply this thing by 2, you get exactly what we got before. So if you're asked on the test to use as many planes of symmetry as necessary, first of all, you use half of it, just like I did, you split this thing. And then at the end, if it asks you how much force is needed to create this deformation, don't put this number down. Multiply it by 2 and write the answer there, because that is the double of this is what is actually needed to inflict that deformation. Okay, so be careful, because I'm going to ask you in a particular problem how much force is needed to do something. You have to go through this motion. First of all, don't say cancel, say okay, because that will give me a reason to know, or I know where you got your number from. But if I ask you how much force is needed on your paper, you're going to have to write for this particular problem this thing times 2. All right, in this particular problem, please. Okay. All right. So that takes care of this problem, and good luck. This takes care of this lab